Go ahead. All right, so our field trip today is a fun one. We're heading up to the Highlands area of North Carolina, and this part of the Blue Ridge exposes metamorphic rocks and synmetamorphic intrusions. So we're going to be really focused on one synmetamorphic intrusive body called the Whiteside trondhjemite. I'll be referring to it as the Whiteside pluton. In the literature, it has been referred to as the Whiteside granite, although it is not granitic in composition. And this intrusive body was intruded during a metamorphic event. It has subsequently been deformed by a second metamorphic event, and it actually postdates a previous metamorphic event. So there's a complex history of deformation that both postdates, is synchronous with, and predates the intrusion of these igneous bodies. So today, some of the major rocks and textures that we're going to be focusing on is we're going to be looking at the boundaries of these intrusive rocks, and we're going to try to get our hands on some of the rocks both within the intrusion, along the margins of the intrusion, where the heat from the intrusive body has caused some partial melting of the host rock, and so we see some really cool migmatite textures in this transitional boundary zone between the contact of the Whiteside pluton and the country rock, which in the areas we're going to be visiting are the ash metamorphic suite rocks. The ash metamorphic suite rocks are similar. They are basically the same as the Tallulah Falls Formation as it's mapped here in South Carolina and in the Clemson area. So these are basically the same formation, but they're given different names. In this region of South Carolina, it's mapped at and named Tallulah Falls, but up in North Carolina, it's called the Ash Metamorphic Suite. The ash metamorphic suite is quite variable. There are gneisses, there are schists, and we think that the protolith for these rocks are sedimentary. They were likely deposited on the seafloor, and more kind of quartz-rich gneissic portions were likely sedimentary rocks with a sandier protolith, and other parts of the ash metamorphic suite and Tallulah Falls Formation are much schistier, and some contain aluminosilicate minerals like sillimanite, garnets, lots of muscovite, stuff like that. And we think that the protolith for those portions of the formation was likely more of a shaly protolith. Also within the Tallulah Falls and ash metamorphic suite, you can see amphibolites, which likely represented basaltic units that were either intruded into the sedimentary protolith as dikes, or perhaps were lava flows on the seafloor. So we're going to get some practice today thinking about metamorphic rocks, identifying some metamorphic textures, and seeing what this intrusive body that we call the Whiteside pluton or the Whiteside trondhjemite. Trondhjemite is a type of igneous rock, and we'll explain that on a stop on the field trip, what exactly a trondhjemite is. We're going to be thinking about how these units are expressed in the landscape, and they tend to form these large high elevation structures that have a dome-like shape, and Whiteside Mountain is one really spectacular example of one of these landforms that is underlain by the Whiteside plutonic body and then capped by country rock that was basically making up the roof of the magma chamber. So that's our ultimate goal. It'll be the final stop on our field trip. We'll be summiting Whiteside Mountain and doing a really great 2-mile hike, loop hike along the cliff face of this like very steep-sided elongate ridge feature. I'll pause. All right, so the very first stop on our field trip, we're actually not going to get quite into the Whiteside area yet. We're going to stop along the way at the Toxaway gneiss. So the Toxaway gneiss is exposed in the area where we're going to visit it in a gneiss dome. And this gneiss dome is actually kind of elongate, and the foliation dips on all sides away from the gneiss dome. And it is, let me draw a map for you here to show where we're going, where this first stop is in relation to the major geologic features and structures of the area. So this is a very generalized map of where we're going to be headed. This line could be a little steeper like that. This is North Carolina, so what I've drawn here are state borders: North Carolina, Georgia, and South Carolina. And the Toxaway gneiss, the first geologic unit that we're going to be visiting today, is exposed here in the Toxaway gneiss dome. It is flanked on all sides by Tallulah Falls Formation, and this is located in the footwall of a thrust sheet. Is that right? So this is the Brevard Thrust Fault that's nearby. The Brevard Thrust Fault is an important, regionally important structure. It extends all along the Blue Ridge in the southern Appalachians. And it is the easternmost large thrust fault in this region. Now, later in the day, we're going to be exploring the Whiteside Pluton. And the Whiteside Pluton is exposed kind of around here in the Highlands area of North Carolina. There's a few other important plutons. Way over here is kind of a skinny pluton. It's actually even further away. It's like way over here. It extends off the boundaries of my small map as I've drawn it. It is called the Rabun Pluton. And each of these are dated at different ages. And then all the way on the side is another thrust fault. That's called the Chattahoochee Thrust Fault. So this is Whiteside. And these are the features that we're going to be visiting today. The Toxaway gneiss dome first, and then we're going to spend most of our day exploring around the Whiteside Pluton body. So our first stop, where we're gonna, the next thing you'll be seeing is the Toxaway gneiss. So stop number one is located something like here, right inside the Toxaway gneiss dome. The Toxaway gneiss dome is basically kind of looks like this. The foliation is dipping on all sides. It's more steeply dipping towards the northeast, more gently dipping across this part of the structure towards the southwest. And so we're going to be visiting this, taking a look at the metamorphic texture, the mineralogy of the rock, and we're going to keep this in mind and compare it to the other meta-igneous rocks that we see when we get up into the Whiteside Pluton. The Toxaway gneiss has been dated at 1.1 billion years old. And this dating was done by dating zircons. Zircons are an incredibly useful geochronometer. It's complicated dating metamorphic rocks that have undergone multiple phases of metamorphism, as these rocks have. It's complicated. But our best estimate and the interpretations of ages that have been gotten from zircons from this unit is about 1.1 billion years old. Now compare this to the Whiteside Pluton, where we're going to be later today. The Whiteside Pluton has been dated at 466 million years old. So these are very different ages. And the Toxaway gneiss dome is a little bit of a riddle. It's located very close to the Brevard Fault, and as such, it was basically thrust into place, transported from the east in these large thrust sheets. So each of these thrust faults is dipping eastward, and the Toxaway gneiss and everything basically in between the Chattahoochee thrust and the Brevard thrust is part of a large thrust sheet that was transported in from somewhere towards the east. So we don't really understand where the toxaway gneiss came from, what its roots are. It's basically chopped off by a thrust fault at depth, and so it's a bit of an enigmatic feature. But one question I think we can ask is the protolith of the toxaway gneiss is it a sedimentary protolith or an igneous protolith? Is it a metasediment, in which case we might call it a paragneiss, or is it a meta-igneous rock, in which case we'd call it an orthogneiss? So maybe that's a question that we can try to answer by looking at the rock's mineralogy at the next stop. All right. So we'll end that here, and next time you see me, I will not be on Clemson's campus. I will be with the class at our first stop at the toxaway gneiss. FYI, the second stop that we're going to make, just while we have the map up, the second stop that we're going to make is going to be about here, just off the toxaway gneiss dome in the country rock that it punched up through. So the country rock that surrounds the toxaway gneiss on all sides is the Tallulah Falls. Now the Tallulah Falls formation eventually is just basically reclassified, as I said, as the ash metamorphic suite. So later in the day when we're working around the Whiteside Pluton, this country rock around the Whiteside Pluton, we're going to be calling it the ash metamorphic suite, but it is extremely similar rocks. Basically it's the same formation. All right then, we'll see ya. All right, you guys, what do we think? What are the textures you see here, and what are the minerals that you see here? Biotite, fair amount of biotite, right? You got some muscovite happening in there? Cool. Feldspar, yeah, what kind of feldspars do you see? Do you see more than one? How can we tell the difference? How do you know what's plage and what's K-spar?
One has striations, one has porphyry, right?
Well, sometimes. That can be something that you can use to distinguish these minerals. Often when it's fine-grained, it's difficult to see the striations that typically form on the surface of a plagioclase crystals. If you get a good one where you can see striations, that's like awesome, and I get very excited about that, but unlikely that you see that if the crystals are super fine-grained. And same with the feldspar, the potassium feldspar. Potassium feldspars may have perthitic texture, but they don't always, and it won't be obvious, especially if the crystals you're looking at are small. So in this rock, how did you tell the difference between plage and K-spar? Because I think it's difficult to use those characteristics. What do you think?
I could tell in thin section.
Yeah, you can tell in thin section, but unfortunately the geologist has to be able to tell in hand sample. What about color? Right? I mean, of course, these feldspars, they're similar minerals, but K-spar and plage usually have colors that are a little distinctive from each other. Plagioclase is typically whiter, especially if it's weathered. It takes on a milky white color. K-spars tend to be, or they may be more grayish, may have a little pink. Is the feldspar in this, the K-spar in this rock very pink to you? No, but there's some gray stuff in here. There's gray stuff that doesn't look like quartz. How can I be sure that some of this gray stuff in here that is K-spar is not quartz? What'd you say?
Transparency.
The transparency is important. Quartz tends to be more translucent. So in the rock, it will look more gray. And that's because it's more translucent, so you're kind of seeing like a shadow in the mineral that makes it look kind of grayish in the rock. And what else?
Is it too fine to look at habit?
No, you should be looking at the shape of the crystals for sure. And in particular, there's one really major difference in the way in the shape of a broken piece of quartz versus a broken piece of feldspar.
Feldspar would be more blocky.
Blocky, exactly. And what about cleavage?
90-90?
Yeah. Feldspar has cleavage, right? It has 90-90 cleavage. And the quality of the cleavage is pretty good. So like I'm just looking at this piece that I picked up, and I can see kind of a little bit of kind of peachish gray colored feldspar. And I know that it's feldspar because it has great cleavage planes. You can often look for the cleavage in the rock by rotating it around a bit in the sunlight. And if it has a good cleavage plane, you'll see flashes. I call these cleavage flashes. And it's where that perfectly planar cleavage surface is catching the light and reflecting it back at you all at one time. So the whole surface will flash at you at the same time because it's perfectly flat, like a mirror. Quartz doesn't have that, right? What does quartz have instead of cleavage? It's got conchoidal fracture. So that's going to make the surface of the quartz look, in hand sample, like maybe a little wavy, uneven, could be a little smooth, right? But it's not going to have cleavage planes. Is there much quartz in this rock? What'd you say? A little bit. Yeah, there's a little bit of quartz in here. I can see some little guys that are they're looking to me like they're kind of a little more sparkly, and that's because the surface is uneven and a little wavy. So I'm not getting a big flash off the whole surface at one time, but I am seeing that it has a very vitreous luster. So yeah, and it's kind of gray in color and looks quite translucent, transparent. So yeah, there's some quartz in here too. So we said that we had both micas, both feldspars, and quartz in this rock so far. Anyone found anything else? Little bit of garnet in some portions of this. All right, fantastic. Anything else? It's pretty simple. I think that's really all that's in here, right? Our feldspars, our quartz, our micas, and some garnet. I don't see any hornblends. I don't see pyroxenes. That's it. Just those things. And so, I asked you guys to think about the protolith of this rock. And when we're looking at metamorphic rocks, we interpret the protolith mainly from the composition of the rock, and we try to understand the composition through its mineral assemblage, right? The minerals present. So if a gneiss has a sedimentary protolith, if it's a very sandy protolith, what would be the dominant minerals you'd expect to see in the gneiss? Yeah, a lot of quartz. Do you think that this gneiss has enough quartz in it to be like a sandy protolith? No, probably not. If it's a shale protolith, then we'd expect to see what types of minerals? Shales are awesome because they have a lot of aluminum in them, right? And I mean, they're full of all these clay minerals, and clay minerals have complicated chemical formulas. They are kind of garbage bags. Like, they have a lot of different types of cations, different elements in them. So we get more of a variety of minerals out of rocks that have a shale protolith. Like, what are just some minerals that you might see in a politic, that means a shale protolith, a politic metasedimentary rock? I'm looking for minerals that have aluminum in them. Yeah, Cole, I hear you whispering it. Aluminosilicate minerals, what are some of those?
Kyanite, sillimanite, and andalusite.
Yeah, kyanite, sillimanite, and andalusite are our three aluminosilicate minerals. They are polymorphs of each other. Wait, is that the right word? Yeah, polymorphs, which means they have the same chemical formula but different crystalline structures. And which one you get depends on the pressure temperature conditions. They're really awesome minerals. Metamorphic petrologists love these aluminosilicates when they're present in the rock because they allow you to get good information about pressure and temperature. Because the boundaries, like on a pressure temperature diagram, on a phase diagram, between where these three minerals are stable are well understood. None of these minerals exist in this rock. Other kind of minerals that we might expect to see a lot of in a rock that had a shale protolith includes maybe things like starolite, if it's a kind of a medium grade, lots of garnet. Now we've got a little bit of garnet in this rock, but I don't think that we have enough of the other aluminum-rich minerals for me to confidently say that this rock has a shale protolith. So what's another option?
Granite?
Yeah, an igneous protolith of a felsic granitic type rock. We'll call it a granitoid, right? Because I don't know its exact composition, but yeah, an igneous rock. Now, we have found that this gneiss It did have a few garnets. Doesn't look like garnets are very widespread, right? I've picked up a lot of pieces. I haven't found garnet yet, but I believe it if there were garnets in some places over there. So there's a little bit of garnet maybe spread throughout this guy. We mentioned that some people saw a little bit of muscovite. That's a relatively aluminum-rich mineral. And so the presence of those minerals doesn't mean that it doesn't have an igneous protolith, because our igneous rocks, they can come from melting a variety of different sources. So often, like if you found a granite that had a little bit of muscovite in it and a little bit of garnet in it, that granite we often interpret like the presence of some of those aluminum-rich phases to mean that the granite came from melting a sedimentary rock. So its magma source was partial melting of a sedimentary rock. We call those S-type granites. I-type granites they lack those minerals. So I think a lot of granites end up being I-type granites, and we take those to mean that they formed from melting maybe more felsic material, partial melts of continental crust, or fractional crystallization, of some more mafic composition of magma that segregates out this like felsic melt. Cool. So that's my interpretation of this toxaway gneiss. It's likely an igneous protolith, and if we see a little muscovite, a little granite, perhaps that igneous protolith ultimately came from the partial melting of sedimentary rocks. So that's something that we can kind of think about. And there might be other ways to try to test that, to try to understand that. You okay?
Yeah. Bird is snail.
All right. All right, what about the texture of this rock? Did we decide that this rock had a foliation?
So foliation, not really very much lineation.
Not very much lineation. I agree with that. If you were looking for a lineation, where would you look for it? Just kind of want to make sure everyone's kind of practiced at looking at rocks like these. Where do I look for a lineation?
When you kind of find a repeated structure just around the whole rock.
Yeah, exactly. When you're trying to look at the texture of the rock, its foliation, its lineation, you need to look on multiple sides. So right here, like this rock I'm standing on, you can see a stripiness to the rock, but this stripiness that I'm standing on is the foliation surfaces on end. And the orientation of those foliation planes are about like this. If I want to see if it's lineated, I need to look on the surface of like a nice, smooth, clean foliation plane. And when you try to get those views, where you try to pick up a piece of the rock, look down on the foliation surface, you got to make sure that you're not looking at an erosional face where you're just seeing foliation planes intersecting with an erosional surface, because that will make it look striped, but it's just an intersection lineation, right? The appearance of lines on the rock face, but it's just because you have the edges of the foliation planes intersecting with that cut or eroded face. So I think I can see some of that going on here. When you get down on a foliation surface that looks pretty smooth, like maybe this one, there's not a strong lineation, which means that, like, what does that mean? Why is it important to think about foliation or lineation in these rocks?
The degree of metamorphism?
Yeah. The presence of a foliation tells you about the metamorphic history. The presence of a lineation tells you about just like a stretching history of the rock, right? Lineations in metamorphic rocks are typically, like the type of deformation that forms them is a stretching deformation. And so often rocks that are like in shear zones have a strong lineation. So one thing that might be interesting if we had more time and we wanted to really dive deep into the toxaway would be to pay attention to how the fabrics change as we move from the edge of the gneiss dome near the contact with the Tallulah Falls into the interior of the gneiss dome. If we see like stronger foliations towards the edge, if we see a stronger lineation towards the edge, that could tell us about whether the gneiss is shearing past the Tallulah Falls. Here in this location, we see a pretty strong foliation, not a very strong lineation, although like, I think this is a nice little piece I've got in my hand here. You can see the foliation planes very clearly. I'll try to hold that still. And when I look down on this bottom surface, I'm looking on the surface of a foliation plane. This is a decent one. I'm looking pretty parallel to the foliation plane here. And you can see that some of the mineral grains appear to be a little elongated in one direction. So yeah, I guess I'd say that this is a quite weak lineation in the rock. But it's not really, it's quite weak. It doesn't really grab you. Make sense? Okay. Cool. So yeah, if we had more time here, I'd be interested to look at more outcrops down on the other side of the road, come up here, you know, and see if there's a pattern in how those textures change as you move from the edge of the dome in towards the center. All right. All right, so we talked about the age of this gneiss and how it was complicated to date rocks like this. One of the reasons, one reason that it's important to try to interpret the protolith of a rock like this, if you're going to try to date it, is it can help you figure out what the zircon ages mean, right? If this was a paragneiss, so paragneiss is the term that we use to say that it had a sedimentary protolith. If I interpreted that this was a paragneiss, I would expect that the zircons in this rock would be detrital grains. What does it mean if I call a zircon detrital? It means that it was a grain, it was a sediment, right? Like it was like a grain, a literal grain of sand, and it could have come from anywhere, right? So in a paragneiss, you might expect to see, when you do zircon geochronology, a wide range of ages, not just a single age. And that wide range of ages means that the sedimentary protolith had zircon sand grains in it that got transported in from just erosion, rivers, wherever it was being carried in from maybe a broad area. But if it's an orthogneiss, orthogneiss is the term we use to say that it had a igneous protolith, we would expect to see maybe a more simple array of ages, where you might have some inherited cores, right? An inherited igneous core that dates back to when it was a granitic intrusion, and then overgrowths, rings around the edges of that zircon, that represent subsequent metamorphic events and zircon growth during those. All right, so in a way, we can make some initial interpretations about the protolith of this rock. If we were doing geochronology, the geochronology might be able to confirm our interpretations, which would be cool. All right. Yeah, and the geochronology, spoiler alert, it has confirmed that. The interpretation here is that this is an orthogneiss. All right then, any questions? Okay, so next, we're going to drive down here, turn right, go a short stretch until you get to a nice scenic overlook area with parking spaces, and we'll pull off there and take a look. So just keep in mind as we're driving that we're coming down off the flank of this gneiss dome, and we're going to kind of wrap around the eastern side of it, and we'll be in the Tallulah Falls Formation, which is the metasedimentary unit that this gneiss dome has punched up through.
All I heard was man, dude. It was so serene. Yeah. That's him right there.
Yeah.
It's clear that it felt safe.
Senor Snow.
I just felt quick luncheon. At least it was quick and easy.
Yeah, he was too young.
Good Gary, bro.
Okay. All right, you guys. This is a relatively brief stop, and we're just taking a look at the overview here and a look from afar at the Tallulah Falls Formation behind us. So, first of all, let's start with the Tallulah Falls, since we've just been talking about the rocks. So, I think that right here, if you want to cross the street and scramble through those bushes to take a closer look at it, you are welcome to. But I don't want the whole class to do that all at one time. The shoulder's not very broad, and it's very bushy. spoiler alert, the Tallulah Falls, it really varies a lot in nature, right? So there's a lot of heterogeneity within the Tallulah Falls formation. It's interpreted as metasedimentary rocks. And we think that the Tallulah Falls formation was basically seafloor sediments. So there are some portions of the Tallulah Falls that are, we think had a more sandy protolith. So they're more quartz-rich gneissic looking rocks. Other portions of the Tallulah Falls had a more shaly protolith. So you get more interesting minerals, garnet sillimanite schists, stuff like that, rich in micas, real sparkly, schisty rocks in other locations. Here, the mineralogy of the Tallulah Falls is a little boring. It's more of the sandy gneissic area portion of the formation here. So it's not that thrilling. You don't have to go and look at it up close if you don't want to. We will see other portions of this formation on our trip today that are much more interesting looking. Now, the Tallulah Falls is equivalent to the Ash Metamorphic Suite. You guys probably were in the Ash Metamorphic Suite yesterday, right? Yep. And these are equivalent formations. They represent the same protolith, the same situation, kind of these sediments accumulated on the seafloor. Some of them might be interleaved with some basaltic material. Basaltic dikes or lava flows end up interleaved with these sediments, and altogether that makes a kind of complicated looking formation of metamorphic rocks that has this kind of sandy gneissy stuff, the more schisty stuff, and amphibolites, which come from the mafic protolith. Now, out in this direction is a pretty view towards the Piedmont. So we're on this like kind of sharply rising face of the Blue Ridge. It has a pretty steep front here, and the rolling it kind of transitions into more rolling looking hills and lower topography in front of this. We call this the Piedmont. This body of water that you see on your left here is called, no, the water out there is Kiowee. This is a smaller body of water, and did I write this? Hold on. Bad Creek. This is the Bad Creek Reservoir. And it's actually kind of cool. So the Bad Creek Reservoir has a pumping station that pumps water out of Lake Jocassee and fills this reservoir. So Jocassee is out of view. It's a little further to the left here. But we have these three big lake systems in our area, reservoirs. Jocassee is furthest up. Well, actually, technically, the Bad Creek Reservoir is the highest elevation. But we pump water up out of Jocassee into the Bad Creek Reservoir, and we'll talk about why in just a second. Jocassee is the next lake, and then that has a dam, and then further downstream is Kiowee, and Kiowee is dammed, and then further downstream from Kiowee is Hartwell. And we will be able to pick out some of these bodies of water from the top of Whiteside later on today. So the Bad Creek Reservoir is kind of cool. Basically, extra electricity that comes from the dam at Jocassee is used to pump water out of Jocassee and fill this higher elevation, smaller reservoir. Then, during periods of like peak use, and did I say that right? No, I'm sorry. It's extra energy from the nuclear power plant, which is located next to Kiowee. That extra energy is used to pump water up out of Jocassee into the Bad Creek Reservoir, and then at times of high energy demand, then they can just use this water storage, flow that through a dam, and generate more electricity when they need it. So it's kind of a cool situation. At certain times then, this Bad Creek Reservoir is completely drained. And I have never been into it when it's drained, but Scott Brame has mentioned that like one time he was able to weasel his way in there when it was drained, and it's really cool, you know, bedrock exposures within this empty reservoir is like really amazing. Yeah. All right, so that's all I want to say here. And just kind of appreciate the view as we're gaining in elevation. And then we're going to continue up into the highlands area now. So our next stop, oops, sorry, this phone out of my pocket. Our next stop is going to be in the valley on the south side of Whiteside Mountain, and we're going to have that, basically the view on the front page of your booklets. That is an aerial image, but we're going to be down there on the south side of the mountain looking up at it, and that's going to be our next stop. So it's going to be like a overview of the south side of Whiteside Mountain. Drivers, the parking at that spot is at this little ancient historical post office called Grimshaw's Post Office. There should be ample parking for us. It's not like this, like a big lot, so just kind of tuck in, but we should all fit. So drivers, on your map, the next stop here should be stop number 3. Oh, sorry, stop 2. This is stop 1A. The next stop on your maps, drivers, is labeled stop 2. So we'll want to navigate to that. Okay?
Alrighty.
Hey guys! Alright, so here's Whiteside Mountain. You can see that this is kind of an elongate shaped mountain with a super steep face. The back side is much less steep, right? Much more gradual climb on the back. So actually our trailhead that we'll do at the end of the day today, the trailhead is on the back side of that. And it's the 2-mile loop, basically just like walks up the back side in that direction, and then it circles around this front face. So we'll walk all along the length of that cliff. And then we take a kind of a steep route down some stairs back to the trailhead. So it'll be really fun. And there's kind of an exclusive little housing community here, so hopefully nobody stops and yells at us. I've been yelled at before for just like standing on this little dike because they're very serious about their private property in this like little housing community. But we should be fine right here. Yeah, so I have referenced that the rocks in this area have experienced multiple phases of metamorphic deformation, right? So how do we understand that? How do we know that the rocks around here have undergone multiple different deformational events? One way that we understand that history is by looking at folds in the rocks. So with a lot of these compressional deformational events, right, the tectonic orogeny consisted of multiple terrains being accreted onto the edge of the North American continent here. And every time that happens, there's compressional deformation and we get some folding. So we think that there are multiple folding events because we see multiple generations of folds. We also see multiple generations of foliation. So when we have a compressional deformational event, we might have buckling and folding of the rock, and we also might have development of a axial planar foliation. What does that mean? That means that the foliation, the metamorphic foliation of the rock that forms, is roughly parallel to the axial surface of the folds that form at the same time. What's the axial surface of a fold? Yeah, it's the plane that connects the hinges of each successive layer in the fold. So the axial surface is an imaginary surface that bisects the fold, that cuts it in half. So what do we see if we have multiple generations of folds? You end up seeing folds that in turn get folded by younger folds. So we name, like when we have this type of situation, we assign the folds names, these like kind of a numbering system, where the oldest folds we call F1, and the next set of folds we call F2, and then in this case, in this area, we have 3 different folding events. So the youngest folds we call F3. And each of these sets of folds has a foliation that's parallel to the axial surface of the folding. And those foliations we give the same number system to. So the letter symbol for a foliation is, we usually use the letter S. So the foliation that's parallel, that formed during the first folding event, formed during F1, we call S1. So that is a foliation in the rock that's parallel to the axial planar surface of the oldest fold event. Now, in these rocks around here, the S1 foliation is typically a compositional foliation within the ash metamorphic suite, or gneisses, whatever rock it is, whatever rock type. It's usually compositional banding that is, part of it is inherited from the protolith, and that is typically referred to as S1, the oldest foliation in the rocks. Also, sorry, Kyle I just realized I think I might have turned this off in the car. I hope this was working.
This one I think is on.
Okay, I think I turned mine off. I can voice over that at home if need be. I'm so focused on you guys, I forget that I'm also have to record for our online students. I'm just too in the moment here. Okay. So what do our folds look like when they get refolded by younger generations of folds? So we've got F1 and S1, the foliation that goes along with the F1 folds. And then we've got F2 and S2, which is a second foliation that overprints the first. That's more parallel to the axial planes of the second generation of folds. And then we've got F3 in this area. So basically, our F1 folds, maybe we take a fold and we fold it like this. So here's my folded layer. If a second generation of folds folds this fold, then maybe an F2 fold might end up looking like this. Let's see if I can even do this properly. Like that, pretty much. Where this outline was the first fold, and now that fold has been tacoed in this direction, right? It's been folded again. And then if you have the third generation of folds, the F3 folds, things start to look complicated, much more complicated. So in an F3 fold, like maybe we've got folds whose axes are this way, we started with this, and then we start to basically imprint like folds along the pre-existing folds. Honestly, it's like so hard to draw. Things get really crazy. This looks like seaweed. That's terrible. Here, this is better. I'll resketch these. Yeah, let me redraw these. I'll use the sketch that I already made that I took more care. So here's our F1 fold with the F1 fold axis. And if I fold this with a new fold axis that's cutting through this way, I would get something that looks like this. Right? So this is the F1 fold axis that has now been bent, and this is the F2 fold axis, right? That has folded the F1 folds. And then the F3 folds, let's say I'm going to make my F3 folds cut across kind of in this general direction. I'll end up with a situation that looks like this. Where I had my original F1 fold axis that is now in the middle of these originally folded layers, right? That's F1. F2 fold axis has now been bent by the F3 folds, and the F3 folds are cutting through straight like that. So it gets complicated, and you can imagine that with each subsequent deformation event, it gets more difficult to identify the older folds. That said, there are places around here where people feel like they can confidently see hinge axes of the older folds. And so if you guys look at the geologic maps in your field guides, some of the geologic maps will have the fold axes labeled, show where there's an F1, F2, and F3 fold axes. Now, around here, the F2 and the F3 folds, their fold axes both generally trend northeast, and they end up controlling most of the regional metamorphic foliation. So when we just walk around and when we go up there and pick up a metamorphic rock, the schistosity, right, the mineral growth, most of the foliation that we're seeing is the youngest foliation that's overprinted the older ones. Hopefully on a couple of stops we'll be able to try to distinguish between foliations of different age, but a lot of what you see is the youngest foliation. Now, since the orogenies that metamorphose these rocks, we have seen uplift and erosion and a lot of fracturing. So actually one of our next stops will look at, basically we're going to kind of get up close to the side of one of these exfoliated domes and see some vertical fractures where the wall rock on the, like against a head wall is basically spalding off. And so we're going to be able to walk through some wide vertical fractures. It's kind of a fun playground feeling area called Granite City. It's not actually made of granite, but that's what the uneducated call any crystalline, igneous-ish looking rocks, of course. The rock that will be in there is actually the Whiteside trondhjemite. Okay, so I'm using this word trondhjemite. I actually haven't said it yet. What's a trondhjemite? It's an igneous rock, right? It's a type of igneous rock. Does everyone have a ride in the rain, or some people have ride in the rains? Well, if you do, at the end of your geologic themed Rite in the Rain book, you might see the coarse-grained felsic igneous rock classification diagram. It's a diamond shape. So even, you know, we don't, sorry, truck. You don't have to be staring at it right now, but just to remind you, you've probably seen it before. This classification diagram is two ternaries arranged on end in a diamond. And you've got quartz, plage, alkali feldspar, which is K-spar, and down on this bottom, F stands for foid. These are feldspathoids. And a lot of the igneous rocks that we commonly deal with plot in this upper triangle. Any igneous rock that has K-spar, plage, and quartz would plot somewhere in here. And a tonalite plots in this area of this triangle, right here. If it plots in there, it's called a tonalite. Just to put this in context with some other common igneous rocks, granodiorite plots right there. Granite plots in this area. Down on the bottom, you've got a few different varieties of monzodiorites and monzonites across the bottom. And these igneous rock names we assign based on the relative abundance of quartz, plagioclase, and K-spar. So a trondhjemite is a type of tonalite. If you look at your book, for one of these stops, let me flip through, you'll see this ternary diagram. And this ternary diagram is a little different. We're looking again, in this diagram it doesn't have quartz on it. It's just showing three types of feldspar, orthoclase, albite, and anorthite, right? So albite and anorthite are two flavors of plagioclase feldspar. Albite is sodium rich, anorthite is calcium rich. And so basically the difference between a trondhjemite is a type of tonalite, but it's differentiated from a tonalite by the proportion of albite to anorthite, basically. So trondhjemites have mostly albite and not very much anorthite and not very much orthoclase, not very much K-spar. So in a trondhjemite, you know, it's a tonalite, so it has between like 20 and 50% or 20 and 60%. Did I say that right? Yeah, between like 20 and 50% quartz And then it has mostly, of the feldspars, it's mostly albite plagioclase. All right. So, most of the Whiteside pluton is classified as a trondhjemite. There are portions of the plutonic body that are classified as a granodiorite, which means it has a little bit more K-spar in it, but most of it is a trondhjemite. So up behind us here, what we can actually see on this mountain face is we're looking at the Whiteside pluton, which we see low down on the mountain face, like this kind of sloping thing that's sloping steeply towards us that looks like it has like watermarks dripping down it on the bottom right of the view. That is part of the Whiteside plutonic body. And then above it, where you see a lot more rock that looks like it's horizontally layered, and you can see some white streaks, some of which look kind of folded, but it's much more horizontal. That is actually the overlying country rock. So the Whiteside pluton in this mountain is making up the bottom part of the cliff face, and it's about halfway up the cliff. It's about right where you see the transition from, it's kind of where those trees are halfway up the cliff on the left, right where the trees that are in the middle of the cliff face pinch out. There's kind of a boundary between dark stained rock below that looks quite homogeneous, and then above there's rock that is, a lot of that staining has been removed by weathering, so it's a little brighter looking, and it looks much more heterogeneous, right? It looks layered, there's like these kind of white segregations looking like it's going through it, and that's the transition between the intrusive body and the overlying country rock that forms the cap on Whiteside Mountain. So what is the term that we would call that cap of country rock if it is just basically sitting on top of an intrusive body like a hat? That has a name, kind of a structural name. It's called a roof pendant. So that's what we're looking at, a roof pendant of country rock. So you have an igneous intrusive body, it intrudes, but then erosion strips away everything else, removing the country rock around it, but just leaving a little hat of country rock on top of the intrusive body. So roof pendants are common in places where you had intrusive bodies and then followed that with uplift and erosion, stripping down and incising into those deeper structural levels. Cool. So here we have a metamorphic roof pendant. And what else can we say about the Whiteside pluton from this view? It's very tabular. It has this flat shape. If you just with your eye try to trace the contact between that homogeneous looking stained and streaky stuff on the bottom, which is the plutonic rock, the trondhjemite, and then the more heterogeneous looking streaky, stripy, horizontally striped rock above, that is the country rock roof pendant, that contact is pretty flat looking. And actually, the Whiteside intrusive body is tabular over a pretty great distance. This is just one exposure of it, but we see the exact same rocks farther to the east that is presumably a continuation of this tabular body, but it's just been eroded through in some places by the river systems. So some of the places in Panthertown where you guys were yesterday, where you saw the Whiteside plutonic rock, you were working in the same body, but just another part of this tabular intrusion. And the other thing that I want you to notice here is like those white segregations that you can see in that bright white spot on the cliff face. That is actually a fairly thick zone of migmatite. So the Whiteside intrusion, based on the migmatitic textures that we see, and so I mentioned this term earlier, but migmatite is a partially melted metamorphic rock. It got up to such high metamorphic grade that it began to partially melt, and we're kind of on this borderline of, what do we call this? Is this igneous or is this still metamorphic, right? So we form these segregations of white rock, call them leucosomes. Leuco just means light in color. Zome just means body, so they're white bodies. And these are separated by melanosomes, dark bodies, of the mafic minerals that did not melt because they had a higher melting temperature. And so this migmatitic zone includes complicated relationships between these partial melts and the metamorphic host rock. They look kind of messy and squiggly, and it's actually kind of unclear how much of that light-colored stuff formed from partial melting of the host rock and how much of it is actually like dikelets and sills that are coming off of the Whiteside pluton. There are some places where it's hard to differentiate between those two things. Whether the Whiteside pluton, it was actually intruding, because it intruded during the deformational event, whether it was intruding and just like squeezing in between the layers of the host rock, forming sills, or whether a lot of these light-colored bodies are partial melts of the host rock. All right. So one cool thing also, just tying this Whiteside landform into the structural context of this area, the shape of this Whiteside mountain is really controlled by the youngest generation of folding. The F3 folds are upright folds, relatively open. So what does that mean? First of all, let me step back. The older folds in this area are more isoclinal fold. And what is an isoclinal fold? An isoclinal fold is one that looks like this. It's basically a fold that is really tight and really long, and it is totally flipped over on its side. So we call that an isoclinal fold. How is that different than what we would describe as an upright fold? Upright folds, actually, really part of the definition of an isoclinal fold is that the axial plane, the axial surface of the fold, has been tilted on its side. So an isoclinal fold, that axial surface is basically totally flipped over. It's flat or horizontal, or, I mean, the plane could be vertical, but the fold axis is vertical. Does that make sense? Which is the hinge. Okay. An upright fold means that the fold is upright and open. So the axial plane is vertical or near vertical, and the hinges are near horizontal. Okay? So the F3 generations of folds around here are northeast trending upright folds. And this ridge is a northeast trending ridge line that's actually defined by one of these upright folds. So the Whiteside intrusion and the host rocks that it invaded have all been folded into this like elongated ridge line. It's kind of cool. So the timeline of events that happened here, all these different deformational events and the intrusion of the pluton, just to summarize everything, at 470 MA, we had isoclinal folding of F1. So those folds would basically, how do we date these folds? We try to date the age of the metamorphism of the rocks, the metamorphic rocks that are folded. So we try to identify metamorphic rocks that host the the S1 foliation, that are involved in F1 folds, and try to identify like the earliest metamorphic rocks. So the F1 folds occurred in a deformational event that we think happened around 470 MA. Then at 465 MA, the F2 folds have been dated, and these F2 folds were accompanied by the intrusion of the Whiteside plutonic bodies and intrusion of the Whiteside. So when I say, we said that the Whiteside pluton is syn deformational, it happened, it intruded during this middle deformational event. the F2, that form the F2 folds. How do we know that? Why do we think that it actually happens synchronously with the F2 folding? The reason we think that is that that planar tabular body of the Whiteside pluton is parallel to the axial planar surface of the F2 folds. So it's parallel to the schistosity, to the foliation that developed during that F2 deformational event. So we use that to say, okay, well, if it's parallel to the foliation that formed during this event, it probably intruded during that event itself. And then the last event, the F3 event, happened a little bit later, over maybe a range of dates. We think that this dates to the Akkadian and Alleghanian or Alleghanian orogeny. And corresponded with some basically slow cooling from the peak metamorphic conditions that happened earlier here in the Taconic. So both of these ages, 470 and 465, are part of the Taconic orogeny. And the F1 folds basically got up to like kyanite zone metamorphism. The F2 folds got up to like sillimanite zone metamorphism, so that's a little higher grade. And so F2 was the peak metamorphic conditions. That coincided with the intrusion of the igneous body, the partial melting of the rocks that were close to the igneous body, forming these migmatites, and then from this point on, things started cooling down. We had one more deformational event, the F3 deformation, and that happened during the cooling down from the peak. So there was just one more kind of pulse of compression forming the upright folds of F3. And then from over the next, let's see, from about 320 to 310 MA. Sorry, my board's getting so messy. I didn't bring an eraser. From 320 to 310 MA, we had exhumation and uplift of these rocks that basically cooled them back to near surface temperatures, out of metamorphic conditions. And this happened during the Alleghanian, this cooling. All right. Awesome. Any questions? All right. So there's a complicated history there and a lot of different kind of overlapping fabrics to consider and to try to interpret. But this is, you know, how the geologists that have worked in this area, how they've interpreted these rocks. The history of their interpretation of these rocks has changed quite a bit through time. And so this discussion is kind of outlined in your guidebooks, but I think it's really interesting to think about. Just to think about, like, what would you do if you're a geologist and no one had ever studied these rocks before and you show up in this area? Where do you start, right? People make mistakes and our understanding of the area evolves through generations of scientists working on these and revising each other's interpretations. So early on, like the first person to map in here mapped in like 1907. His name was Keith. And he called these rocks the Whiteside granite. Turns out they're not really a granite at all. So that was a bit of a misnomer. They were reclassified later. But honestly, like the genetic interpretation of the rocks, people weren't really sure about them until much later. So in 1952, another guy came in, studied this area, named Olson, and he reinterpreted these rocks as intrusive. Basically, it was, you know, identified as a granite, but the history wasn't really clear. So he looked at these and said, I think that these are igneous intrusions. The Whiteside plutonic body is a pluton. But then, later, in 1967, someone else came in and decided that these rocks are not plutonic at all. These are metavolcanics. Why do you think he thought that they might be metavolcanics? And it turns out he's wrong, but why do you think he might have thought that? Igneous origin, yeah. We identified that had an igneous origin, but he was trying to determine whether it was intrusive or extrusive protolith, basically. Because these rocks, I mean, since they were intruded during peak metamorphic conditions in the late Taconic, they, you know, were deformed again and remetamorphosed during that F3 event. So they are really technically, I guess, metamorphic. But how would we even go about trying to determine whether this rock, whose mineralogy certainly suggests it had an igneous origin, how do we determine whether it's volcanic, extrusive, or intrusive? That's a good idea. So you could look for volcanic textures, like a glassy ground mass, right, a porphyritic texture, but in metamorphism, all those textures can be erased, right? The rock can be completely recrystallized, losing those textures. Okay, so that's kind of hard. Same with the grain size. The grain size changes during metamorphism. If it wasn't metamorphosed, this would be an easy distinction to make. But it's difficult to distinguish between meta-volcanic rocks and meta-intrusive rocks. It's very difficult. The guy who decided he thought that they were volcanic, he said this mostly because of the orientation of the intrusive body. He noticed that the Whiteside granite, what they're calling it, right? The Whiteside trondhjemite body was parallel to the foliation in the country rocks above and below. So basically he assumed that that meant that they were originally emplaced as surface lava flows because they were parallel to the rocks layering above and below. But turns out that's not a good assumption. Just because they're parallel to the metamorphic layering above and below, that does not mean that they were deposited on the surface and that the rocks above and below, back when that was still sediments, the layering might not even have the same orientation as it does now that it's a metamorphic rock, right? So this new interpretation was revised once again, reinterpreted as an intrusive body, which everyone's much more comfortable with now, based on new information, basically refuting these earlier claims. And so the new stuff that we use to try to say, nope, that guy was wrong, this is intrusive. Of course, we explain the tabular shape by saying, oh, well, it intruded during metamorphism, and that's why it's parallel to the foliation. But beyond, people also looked more closely, and they saw big hunks of the ash metamorphic sweet rocks, big hunks of the country rock floating in the plutonic rock, right? In the Whiteside pluton. That's pretty good evidence that the Whiteside rock is intrusive, right? And what they were looking at are xenoliths of country rock, big hunks of country rock that's basically broke off the walls of the magma chamber and floated in. And they also saw a lot of like little dikelets extending out from the plutonic body and invading the country rock in kind of a complex way. And that would be very unlikely if it was a surface lava flow with like an unconformable contact on the top with more sediments laid down above it, right? We wouldn't expect to see like these kind of fingers and stringy dikes extending out from the pluton into the country rock. So people got back to the basics. They looked at these textures and said, nope, that guy in 67 was wrong. These are intrusive. Yeah, and so that reinterpretation happened in 1997. So, I don't know, it's kind of amazing the time scales at which we figure out this stuff. And now we can all sit here and summarize this history of all the different thoughts on these rocks in a 10-minute lecture. But just took time for people to get out here and do the work that was needed to make these interpretations. All right. So the Whiteside pluton, zircons give ages of about 466 MA, plus or minus about 10 MA. So these are Ordovician in age. And most of them within the Whiteside pluton have cores that are Mesoproterozoic. So what does that tell you? At the very least, it tells you that this Whiteside trondhjemite, this plutonic body, moved up through very ancient crust on the way into its current position. So those 466 Ma rims on the zircon are what we interpret as the original igneous age. And then the cores are Mesoproterozoic, and we interpret that to think that the Pluton, as it rose up through deeper levels of the crust into place, it moved through Mesoproterozoic rock and melted some of it and incorporated some of that rock. And some of the zircons did not melt completely. So they ended up forming these little seed cores that later zircon could crystallize around and nucleate on, growing rims around it during the igneous crystallization. Awesome.
What are those first two blanks? Miller and others showed it to be mostly blank with minor blank.
Good call. That's referring to the rock names. So what goes in those two blanks are mostly trondhjemite with minor granodiorite. So that interpretation of actually that's kind of interesting to point out that it was Miller, and he's the guy who was working in 1997. He's the one who took a closer look at the mineralogy even and classified these rocks not as granites, as people have been calling them, but as trondhjemites, right, which is a type of tonalite, and some parts of it are granodiorite. Yeah. Cool. Are there any other blanks in the guidebook that I've missed? Excellent. Okay. So when we look at this rock, I just want to make sure, I think that this seems obvious to me, but it might not be obvious to everybody. You should be tuning in to the horizontal layering, right? Most of that horizontal layering is in that transition, that migmatitic transition zone. And then in the top, you kind of get out of the migmatites. You see less of that white striping in the mountain. And then you're into the more coherent ash metamorphic sweet rocks. And all of the striping that you see on that face that's vertical, that's just from water dripping down the cliff face. So it's just staining, basically kind of like a desert varnish type thing, except we're not in the desert. It's just staining from water pouring off the cliff and draining down its sides. Whiteside is a famous place for rock climbers to climb. Actually, sometimes when we're out here, we can see rock climbers on the face. So keep a lookout for them. I've seen them before up there. And are people interested in climbing? Yeah, it's not something I know a ton about, but I've been told that basically to climb these mountains around here, there's really excellent world-class places to climb here on these steep-faced cliffs. It's difficult climbing up through the Whiteside plutonic rock, the trondhjemite. There's not a lot of handholds, and most of the climbing is traction or friction climbing where people are going up the water grooves. And then once you get up past the Whiteside plutonic body into the ash metamorphic suite, then there's abundant handholds, and because the rock is much more layered and heterogeneous, so there's differential weathering that makes it much easier to climb, apparently. Cool. Are there any questions? Okay, so just to let you guys know, when we get to the Whiteside mountain hike, we're going to start in a forested trailhead parking lot. We're not going to be able to, well, actually, it's actually pretty cool. There's a gravel road cut into the back side. So that first part of the hike that we'll do together, there are some road cut exposures on the hike where we can see the migmatitic zone. So on our hike later, though, we're going to start above the Whiteside plutonic body. So you can kind of visualize its elevation here. The starting point of our hike is actually above that contact on the backside of the mountain. And so we're going to start in the migmatite zone. We're going to see good examples of the leucosomes and melanosomes as we start our hike. And then we're going to get out of the migmatite zone, and we'll end our hike on the top within the more coherent ash metamorphic suite rock. All right then. Now our next stop is to look at the Whiteside trondhjemite. So we're going to Granite City. So that's the place that I mentioned that had the vertical joints where basically we're kind of getting up against the steep face of one of these balds, one of these domes around here, and we're in the Whiteside Trondhjemite rock, and it's like spalding off of the face, and it's going to be a cool place to walk around. The Granite City, our next stop, we're going to get onto a gravel road and drive on a gravel road for a little bit. I don't remember the parking being too difficult on those gravel roads. Like, find a place, when you see me pull off, just look for a place to safely pull off and leave your car. You might just kind of have to like park on the edge of the gravel. Okay? All right. Well, first of all, let's set the stage. We're at this place called Granite City. We're not standing on granite, we're standing on the Whiteside Trondhjemite. So, what's in a Trondhjemite?
More feldspaths.
It's particularly not very much orthoclase, not very much K-spar, much more plage, and of the plage, most of the plage is albite, not anorthite. That's what makes a Trondhjemite. So basically, like, our Trondhjemite is a tonalite. So on a ternary with quartz, plage, and K-spar on it, it plots over here. So it has maybe a little bit more plage, but the two dominant minerals are plage and quartz. K-spar is not very abundant. And then of the plage, most of that plage is albite, not anorthite. All right, so that's a Trondhjemite. Now, what else do you notice about this rock here?
Some mica, like some muscovite maybe.
Yeah, there's definitely muscovite. There's quite a fair bit of muscovite. And then a little biotite too, so the black speckles are mostly biotite. But yeah, I'm pleasantly surprised by how mica rich, how muscovite rich this is. That's kind of cool. And it's very weathered here, right? Like all the pieces that we've broken off that are in people's hands, we got a lot of this red staining, this orange staining. So we have oxidation of the mafic phases, and the staining is just a chemical weathering thing. When we see places where the Whiteside Trondhjemite is fresher, it does not have this orange staining. And it's kind of clear, not only is the rock has this like oxidation, this orange staining from rusting of the mafic phases, it's also quite crumbly. Like, it doesn't actually really take much to break it with a rock. Kind of medium field strength, moderate to low even field strength. It's actually really easy to crumble. So this surface weathering has started to break down the plagioclase, break down the feldspars, and so pretty crumbly stuff. But do you see the quartz in this rock? And do you see the plagioclase in this rock?
Yes.
Definitely see the plage, a lot of plage in here. What would you say is the proportion of plage to quartz in this rock? Well, you've got a quartz vein, so you got a lot of it. But what would you say is the proportion of plage to quartz? Yeah, lots of plage, much less quartz. If you were to put those in a ratio?
80-20.
Yeah. Yeah. Yeah, I think so. Cole said maybe like 80-20. If I'm just looking at proportion of plage versus quartz. And I think that's fair. Yeah. And so that works, actually. That would perfectly put it in the tonalite field, which is why they called this rock a Trondhjemite. Okay, cool. So the main reason that we've stopped here, besides just getting our first look at the Whiteside plutonic body, the Whiteside Trondhjemite, we're here to see some cool fractures. So now, most of the time when we have kind of these dome-shaped landscape features being eroded and kind of incised around the edges, they exfoliate, right? And exfoliation joints are usually subhorizontal. And if they're not subhorizontal, they're subparallel to the topography itself. So you'll get like big sheets of the rock that spalled off and flake off down the side. It doesn't look like a flake when a giant flat slab of rock is sliding towards you, but it's essentially flaking off through the process of exfoliation jointing. So in a place like this, we might expect to see a lot of horizontal fractures. And usually it's uplift and exhumation that causes exfoliation jointing, right? By eroding stuff off the top, we depressurize the rock, and as those rocks are depressurized, they're kind of relaxing, and so the lowest principal stress ends up being oriented vertically, right? Because we are unloading, and so we're taking away weight off the top, so the least principal stress ends up being oriented like this, kind of pointing towards the surface of the topography. And so you get extension fractures, joints. That is a fracture that forms where you just get some separation, just some horizontal or vertical separation, right? Just opening with no movement. And those joints are usually parallel to the topography. But what's kind of weird and cool about this spot is that we're not looking at a lot of horizontal joints here. We have this joint set of vertical joints. And these vertical joints have been basically funnels for runoff for rainwater, and they have been widened through erosion, but the outline of the main joint sets is still really easy to pick out here. So right now we're standing on one, basically right here is one of these vertical joints. And does anyone have a compass on them? Let's get a azimuth, like a trend for this vertical joint set. And we can just look at the wall of these joints and, you know, we can see a bunch of them. Like every little face on this side here has a roughly same orientation. This face, this face, this face, and that one under all of your feet, all pretty much the same. Very vertical looking. And so I just want to shoot an azimuth here and get a general trend for this joint S. 155. Cool. Anyone confirm that? Yeah, so 155 is southeast? No. Yeah, southeast? Yeah. All right, cool. So we've got like a northwest-southeast trending joint set. So you might want to note that orientation. And some of these northeast-southwest, no, I said that wrong. Southeast-northwest trending vertical joints, there's another joint set in here that is oriented orthogonally. So roughly 90-degree angles to these. So that orientation would be like northeast, southwest, right? And so we've got some orthogonal joints that are connecting these widened, like larger, older joint sets. So these vertical fractures are interpreted to basically be a result of the kind of spalding off of the side of one of our dome-shaped exposures of the Whiteside gneiss. There's a steep head wall, which we can't see because it's hidden behind these rocks and behind these trees. We're not very far up the flank of the slope. We can measure in steps how far we walked up the side of the slope, but I don't know if you guys noticed when we left the last outcrop, right as we kind of turned the corner away from the Grimshaw post office, we could see out the car windows another kind of big bulging domey feature that looked like it was made of our Whiteside trondhjemite, and we have basically flanked that and come around the back side of it, and now we're nestled up against the side. So a lot of these vertical joints are basically where we think this trondhjemite is just fracturing and kind of spalding off to the side. Okay, so this is a fun place to explore, so we're just going to get in there, and we've noted the orientation of the fractures. I think that you should describe the fractures, like how widely spaced are they? When we get in and walk around, I want you to think about the spacing in between fractures. So here I can kind of get a visual estimate of the opening of kind of the walkways, but each of these is not one single fracture, right? But they have the same orientation as our vertical fractures, and then they've been eroded out. Like, I think a good place to really think about that is right here where I'm standing, where we can see multiple surfaces of the same fracture orientation, where it's pretty clear that the rock has just been eroded away on either side, on this left side here, right side. Yeah, and so we should expect to see a couple of different sets of fractures. So we're going to kind of walk in. Again, this is optional. If you don't feel like exploring in the rocks, you do not have to. This is really just for fun. I really enjoy this part. But there is some clambering involved, but you can just go as far as you want to. And if you're ever uncomfortable clambering, just turn around and come back the way you came. Okay? So we'll meet here in, you know, when everyone's done exploring. Don't take maybe more than about a half an hour, but we'll probably stay mostly together.
Is there any?
And we'll meet back in. Okay, so what is kind of interesting, if you look in your guidebook, is that the people that most recently mapped this area, they actually did not include this spot within the unit that they defined as the transition unit that was full of migmatites in between the Whiteside plutonic trondhjemite and the country rock, the ash metamorphic suite. This is mapped within the ash metamorphic suite. And I think this is full of migmatite. Do you guys agree?
Yes.
Yeah. So how do we recognize the migmatite? The migmatite has these light-colored bodies, and they look super squishy, and they're usually highly, like, kind of folded and irregular bodies of the of the leucosome, the light-colored rock that represents the partial melt, and then in between is the melanosome or the restite. That's the leftover mafic stuff, or least rock with a higher proportion of mafic minerals. And what's really cool, and if you can see, you can probably even see this pretty clearly from down there. Around the white bodies, the rock immediately surrounding them is much more biotite rich than the rock a little further out. Justin, can you kind of point to some of those relationships so everyone can see them? Yeah, so like right along the edge where he's tracing his finger, does the rock look a little blacker, like right against the white? And then if you point a little farther out into the gray zone, yeah, it's grayer, and Justin can tell you, because he's standing right there, that it's gray because there's more light-colored minerals in it, right? There's more quartz and feldspar mixed with biotite in that more gray portion, and then right up against this little zone of partial melt, like that really black area, all of the quartz and feldspar has essentially been removed, just leaving this concentrated, like rind almost of biotite around this melt pod. And that is really cool, and it's pretty direct evidence that these melts were sourced from right here, from this rock, and that all of the white streakiness you see in this outcrop represents partial melting of this rock in place, which is awesome. So I love looking at migmatites. Just the textures are really striking and beautiful, and the contrast between the light and the dark are really cool. And these rocks formed at very high temperatures, right? They were partially melting, and so we get these textures of like these kind of like wavy, squeezy, folded little leucosomes that are really striking. So probably, you know, I don't agree with how those people mapped, neither does Scott Brame, who wrote this field trip guide and included this stop. Probably this should be, if it was remapped, I would include this as part of the transition zone. So where have we gone since our last stop? Our last stop was in the Whiteside trondhjemite, and then we were snaking along the flat valley bottom for a while, and then we started coming up this hill. So we're going up in elevation, which means we're starting to move out of the top of the trondhjemite, which is a relatively tabular flat body, and into the overlying ash metamorphic suite. So this stop here at the quarry, we're right in the transition zone. We've come up out of the main body of the trondhjemite, and now we're in this migmatized portion of the ash metamorphic suite. And eventually, as we go further up the hill, supposedly, like we should see less and less migmatite, right? If we go further down the hill, we should see more and more migmatite as we get closer to the plutonic body. So that'd be interesting if we had the time and resources to like really try to map out this transition zone. Yeah. So this is a great example of a migmatite. And what's the mineralogy of the white zones? Can you guys see that up here? And you guys who are looking at the other side, what's the mineralogy of the white segregations? Very quartz rich, right? Like, here's a piece. Kyle. Here's a piece. It's just got a lot of quartz, almost 50% quartz, looks like, in some of the pieces that I picked up. Some feldspar, very quartz rich though. And then the darker portions just have a much higher proportion of biotite in them. Whereas right around some of these white leucosomes, at least in this outcrop, you know, it looks like 90% plus biotite. And then it doesn't, you know, it's a pretty thin rind of restite that's super rich in biotite around those melt segregations though. And then the rest of the rock kind of looks like this. Here, Kyle, I'll toss you another one. Whoop, a little darker in color. A greater proportion of mafic phases. Did you guys see anything else cool around there?
I'm not sure what this is. It's
yeah.
Greenish. I was thinking chlorite, but I wasn't.
Yeah.
I can taste all the minerals.
I'm not 100% sure. I need a hand lens to get closer in there. Like, part of it almost looks like green staining over here.
I thought too.
Like, at first I thought, could that be algae, like, that grew in a crack? But this looks like a freshly broken piece.
I broke it
right? So it must be mineral. It could be a bit of chlorite. It also could be epidote.
Yeah, I've noticed.
But it's a little bit the wrong color for epidote. And the portion on the left there where it kind of looks almost like more translucent, it almost looks like green stained quartz. Yeah. I don't know, it's a little bizarre looking. Let's see.
The white is it white planet? White, yellow, and then those are just
All right. Yeah. I think if we're done observing this rock, really, I think the striking things to note are just the texture, the look of the migmatite, how to ID it, and really understanding how this partial melt, this texture forms. So if you guys are happy with this, we can head back to the cars. If I So this is called Sunset Rock, and we have a nice overlook view of the town of Highlands here. So that area, you can see a little steeple and buildings. That's downtown Highlands. And this is a popular spot to just come for a nice view and to hang out, walk the dogs, stuff like that. But it's nice because we've got this kind of bald exposure where we can see a pretty continuous thick sequence here through the ash metamorphic suite. So under our feet, what's the rock type? What would you call this rock?
Mica schist.
Yeah, mica schist. Some of it is getting a little nicey, right? What's the main minerals that you see?
Biotite.
Lots of biotite. What else?
Quartz here and there.
A little muscovite, some quartz, some feldspar.
Yeah.
Awesome, yeah. How many of you guys were looking at the ground on the walk-in? Did you see any other interesting minerals or rocks that we passed over on the way down the gravel road?
There's some like
There was some migmatite at the beginning near the cars. I'm not sure. I don't think so.
I saw some like mica schist.
Yeah, there were some mica schists we came over, and there were some garnet schists. I just grabbed a piece on the way back. Take a look. The garnets are pretty obvious. We can pass this around, but this looks to be a garnet silmonite schist. So how do we identify garnet is pretty easy to ID, right? How do we identify silmonite? Silmonite's an aluminosilicate. It has like a needle-like habit. So when this guy comes around, it looks sometimes similar to muscovite. So the muscovite is the platy stuff. But if you see anything that looks like kind of scraggly needles, almost like felty fibers, that's silmonite. And there's a bit in this rock with the garnet. Sometimes it's easiest to see the silmonite when you look at it from the side, but if anyone's interested, we can just pass that around just to show some of the variation within the ash metamorphic suite. So this particular stretch of the outcrop is mostly biotite, feldspars, quartz, but all down that gravel road, we're walking over the same formation, and it changes. There were portions that were really garnet rich. That guy has a little silmonite in it, as well as garnet, so it's variable. Now, the other reason for coming to this spot is it is one of the places where people have described the overlapping foliations from these multiple deformational events that we discussed. So, the S1 foliation, so that's the oldest foliation that formed at the same time as the F1 isoclinal folds through this area. The F1 foliation is interpreted to mostly be defined by the compositional layering in this rock. So that is defined as the S1 here. That's what people have interpreted. And the S2 foliation is overprinting that. And that is mostly recognizable by the orientation and alignment of the micas in the rock. So I encourage you guys to kind of hunt around over the face of the outcrop. I think a good place to look at it is actually like right under Katie's feet there, where there was kind of a bit of a ledge, kind of a bench. And that seemed like a decently clean place. There's a fair bit of lichen on this, so you want to kind of try to see past that. But I encourage you to look around and see if you can identify places where you can identify the main compositional banding, where you have more kind of quartz and feldspar rich layers alternating with more biotite rich layers, and see if you can see the alignment of the micas at an angle to that compositional banding. The aligned micas, if the angle's not super sharp, if the compositional banding is like this, the mica alignment is kind of like this. So it's at a shallow angle, but there are places where you can convince yourself that you see that. So this is one of these places where, with this good exposure, people have figured this out, interpreted that these are two different deformational events, these overlapping foliations kind of crossing each other. So we won't stay here for too long. I just want you guys to hunt around, look at this rock. As I walked across the surface, there are some kind of cool textures you can spot, places where there's little stringers of quartz and feldspar rich layers that have been stretched out and boudinaged are pretty cool if you can find some of those. And yeah, let's look to see if we can identify those crossing foliations. One defined by the compositional banding, the other defined by the alignment of the micas at an angle to it. That represents these two distinct deformational events, the first and the second. Great. So here, this is very subtle. Honestly, these crisscrossing foliations are quite subtle. But you can see the compositional banding pretty clearly here, the white layers and then the darker layers between. And if you look carefully, the dark layers consist of mostly mica, biotite, and a little muscovite, and the micas are primarily oriented more at an angle like this. So the micas are dipping at an angle to the orientation of the compositional bands that are going like this. So that's the orientation of the micas. This is the orientation of the compositional bands. And it's super, super subtle, but as you look around the outcrop, you do see the same orientations over and over again, where the compositional banding is interpreted to have formed during the first deformational event, at the same time as the F1 folds that we discussed at a previous stop, and the cross-cutting low angle foliation to those compositional bands here, which is primarily defined by the alignment of the micaceous minerals, is interpreted to have formed during the second deformational event. That formed the F2 folds in the region. Okay, so here we can see another compositional band. This is the F1 foliation, and very subtle, but there, the micas in this portion of the rock are at an angle like this. So they're kind of going like this. So that's the S2 foliation. That's younger. So we are just starting our hike up Whiteside Mountain. So students cruising up, they're winding their way, wrapping around the backside of this elongate kind of ridge of Whiteside Mountain, and they're gonna eventually pop up on the top, and we're gonna be above that big cliff face that we saw in an earlier stop. So I'm just gonna pause on our walk up here a couple of times and show you some rocks that are outcropping in the cliff face, like in the road cut here. And I stopped here because there's some cute little pegmatites. So here's a cute little pegmatite that kind of pinches in a tigmatic fold here. That's kind of cool. And a larger pegmatite body here, and more pegmatite here. So what we're walking through right now, like the trailhead was actually above the elevation of the contact between the Whiteside trondhjemite below and the ash metamorphic suite above. So as you recall from the earlier stop, the Whiteside mountain consists of a large tabular body of the Whiteside trondhjemite below, capped by a roof pendant of the ash metamorphic suite. So we are in the ash metamorphic suite, and right now, based on some of these textures, these squishy little folds, I think we want to keep an eye out for some dark melanosomes and some light-colored leucosomes. Keep an eye out for it. We want to see if we're moving up through that migmatitic transition zone like what we saw at the quarry. All right. All right, so we just got up to the top, walked up that gravel uphill, and this is our first view. We're gonna traverse along the cliff face, down the length of this ridge. So just a reminder, here on top of Whiteside Mountain, this all is part of a large F3 fold. So that's the youngest generation of folding that folded the tabular Whiteside pluton and the overlying ash metamorphic suite into kind of just a big upright fold. So the length of this ridge line that we're traversing is essentially following the fold axis, and down the face of the cliff beneath us, like right now we're standing on ash metamorphic suite stuff. So if you pan down just to the rocks, see what they look like. We're looking at more banded gneissic, and as we walk along we might see some portions that are more schistose. There are some very coarse-grained segregations right at our feet that look pegmatitic in texture. And so we're going to be walking over these rocks along the rest of the hike today. The Whiteside trondhjemite will be down beneath us, and so we might get some views of it kind of from the side, but we won't be walking across it because it's exposed in the cliff face. And I don't know if you can walk over there and show just the reservoir where we stopped this morning at our second or third stop, where we were looking up at Whiteside Mountain, just to kind of give a sense of scale. We were down next to that little reservoir this morning when we were talking in the grass. So just another view off the top here. This is a nice clear view of the reservoir where we stopped this morning. So our path, our route on the field trip, we took a curvy, windy road down on the bottom of this valley, and we wrapped around this big dome-shaped knob to the left of us here. And it was actually on the flank of that knob that we stopped at Granite City and checked out those vertical joints. And usually on a clear day, we can actually see all the way out to our local lakes, Lake Kiwi and even Lake Hartwell if it's super clear. But today it's a little misty out there, a little foggy, so we don't have quite as good visibility. But a lot of these dome-shaped features that you see in the landscape around us are also underlain by the Whiteside trondhjemite. And that's really explaining this topography. So here's this eroded out pegmatite. You can see a little bit of it in the walls, that coarse texture pegmatite. But the pegmatite eroded easier than the rock that it intruded, so it's eroded out and formed this little pathway through the rock. And the students are going down there just to look at a little view area that's just beyond those trees.
Be careful here.
Yeah, like a step right here and then we'll go expose it as much as you can.
Okay, I'll take the corners. I'll take the least safe.
Say hi!